Okay, so 5.6 is solving motion problems with parametric and vector valued functions. Back in Calc AB, you did discuss straight line motion or moving along some kind of curve. Now we're going to be discussing the motion along curved paths. It's basically the same thing you did in AB, but now you can kind of more broadly discuss the path of an object. So as an object moves along the curve of a plane, the coordinates of x and y of its center of mass are each functions of time. So the coordinates of x and y are each functions of time. So rather than using f and g to represent two functions and write them as parametric equations, it's a lot easier to write them as vectors. So it's just like a little bit neater and faster. The nice thing about doing this is it's easier to use derivatives for vector value functions, and that helps us find the velocity and acceleration. You're going to see a lot of questions, or not a lot, but like the questions that are talking about particle motion on the AP exam are going to be vector valued functions in BC. So if x and y are twice differentiable functions of t and r is a vector valued function, then we would say r is equal to some x and y. That can be written, again, r of t can be written like x of t, y of t, and all of its derivatives would also follow that path. The speed is taking the derivative of that vector function and then finding the magnitude of it. So the two vertical bars are the magnitude. Magnitude of the derivative. Remember, magnitude is just saying a squared plus b squared square rooted. It's like finding the hypotenuse. So a particle moves along a path defined by r equals 3 sine t over 2 plus 3 cosine t over 2. So basically t is a function of is moving in a ordered pairs. You have one variable, but it's really defining x and y. So if x is equal to 3 sine t over 2 and y is equal to 3 cosine t over 2, in order to generate the rectangular equation, which means not polar, but writing it from going from t, something in terms of t's, to something in terms of x's and y's, then we need to kind of like figure out how we could rewrite this. Dividing both sides by 3. Whenever you see sines and cosines together, it's probably a good idea to use the Pythagorean identity and say sine t over 2 squared plus cosine t over 2 squared. What does sine squared plus cosine squared equal? 1. And sine is equal to x over 3. Cosine is equal to y over 3. You can substitute those values in. Okay, and this kind of looks like an ellipse right now because you have a fraction equals to 1, but the denominators are the same. So when the denominators are the same, you can't tell which axis is the major axis. So let's multiply both sides by that denominator. And you have x squared plus y squared is equal to 9, which hopefully you can identify as a circle with a center at 0, 0, and a radius equal to square root of 9, which is 3. Okay, so this is it in rectangular. Finding the velocity vector and the acceleration vector, and then the speed. Interpret the speed. So first we're going to find the velocity. Remember, v of t is equal to the derivative of r. Okay, so taking the derivative of sine is cosine. Slap the baby. So multiplying the 3 by 1/2. Derivative of cosine, negative sine, don't forget to slap the baby. Okay, so here's our velocity. I would right away just use speed instead, because the speed is finding the magnitude of the velocity. So speed is magnitude of velocity. So we got square root of 3 over 2 cosine t over 2 squared plus negative 3 over 2 sine t over 2 squared. What could we factor from both of these? So factoring out from both cosine squared and sine squared, you can factor out the 9/4. And you're left with cosine squared t over 2 plus sine squared t over 2. Remember, with the Pythagorean identity, it doesn't matter what the argument of the sine and cosine is. It's just the fact that they're both squared. So now you have the square root of 9/4 times 1, because cosine squared plus sine squared is 1, which simplifies to 3 over 2. So speed is 3 over 2. And interpret the speed. I would interpret this as being that the speed is constant. Okay, and last thing, acceleration. Acceleration is the derivative of velocity, or the second derivative of the vector function, but since we already have the derivative of the velocity, since we already have the velocity, it's going to be kind of easy to take the derivative of that. So we get negative 3 over 4 sine t over 2 and negative 3 over 4 cosine t over 2. The 4 is coming from slapping the baby. Okay, now we're going to show the particle's path on the graph to the right. Be sure to use arrows to indicate its direction. It's kind of easier to graph this if I'm using its rectangular form. So using the rectangular form, I know that I'm graphing a circle with a center at 0, 0 and a radius of 3. And finding the show arrows to indicate the direction. So how is the direction moving? Maybe plug in a couple points. Like like find r at 0. So r at 0, back into the original function, vector function. Sine at 0 is 0. Cosine at 0 is 1. Okay, so when time was 0, we were at 0, 3. So we're up here. Then, when time was like, maybe pi over 2 or pi, maybe? Pi, plugging in, I get 3 sine at pi over 2, which is going to be 3. And then 3 cosine at pi over 2, which is going to be 0. So from 0 to pi over 2 is really like at this point, 3, 0. So it seems like it's moving. Oop, clockwise. Clockwise rotation. All right, and our last thing we're going to do for this problem is find the velocity and acceleration at t equals pi. Draw the velocity on the graph above. Really, it's to the right, but whatever. Okay, so we just found, first thing you have to do is find r at pi, which we just did. R at pi. Oh, which was 3, 0. Then, from that point, you are going to graph and find v at pi and acceleration at pi. Okay, so using our velocity vector, we get 3 over 2 cosine, plug in pi, negative 3 over 2 sine, plug in pi. Okay, cosine at pi over 2 is 0. Sine at pi over 2 is 1. So from the point A and V are always plotted with their tail on the position at whatever t value. In this example, we're doing t is equal to pi. Okay, so here's the tail. At this point, this is r of pi. V of pi being 0, negative 3/2 means I'm moving to the right and left 0, and then down 3 over 2. Down 3 over 2 is like down 1.5. Down 1.5. And draw a vector. So this is vector v at pi. Then plugging into our acceleration, we're going to have negative 3/4 sine pi over 2, negative 3/4 cosine pi over 2. Okay, sine at pi over 2 is 1, so we got negative 3/4. Cosine pi over 2 is 0. So again, with our tail on r, now moving to the left, 0.75, and up and down, 0. I'm drawing a vector. That's it. Just make sure that the tail is on whatever t value you're plugging into the acceleration and the velocity. Okay, example 2. Sketch the path of an object moving along the curve. Find the velocity and acceleration vector at 0 and at 2. Sketch the velocity on the curve below. So if it's not something that, notice how on this one, this is not as easy necessarily or like intuitive as the sine and the cosine. So what you can always do if you have to graph these, or if it would just like help to graph, is to set up a table of values. My x coordinate is going to be the I component, and my y coordinate is going to be the j component. Okay, it's not limiting me to only positive numbers, so let's just maybe plug in like -2, -1, 0, 1, 2. Okay, so then we got 4 minus 3 and -2. So we have a point 1, -2. Then as the time is increasing, now we have a point at -2 for x -1. So already, I know it's doing something like this. We get 0 minus 3, 0. Okay, 1 minus 3, and 1. So -2, 1. And then 4 minus 3 is 1, and 2.1, 2. So if you think this looks like a parabola, you're correct. It is a parabola. It's a sideways parabola because you could have said y is equal to t and x is equal to t squared minus 3. So then x is equal to y squared minus 3. It is a sideways parabola. Okay, so then our velocity vector. Velocity vector is going to be 2t and 1. V at 0. 0, 1. Okay, so at 0, what point were we at? When t was 0, we were at the point -3, 0. So we're going left and right, 0 and up 1. This is v at 0. Okay, and then we want to find v at 2. 2 times 2 is 4, 1. Okay, and then v at 2, 1, 2. Going to the right 4, 1, 2, 3, 4, up 1. V at 2. Okay, and our acceleration vector at any time is going to be 2, 0. So even if I did a at 0, I'm going to have 2, 0, and a at 2 is also going to be 2, 0. So left and right 2, right 2, up 0. And from same tail, right 2, up 0. That's terrible. Okay, totally missed. Kind of looks like my parabola was intersecting it, but it would have kept increasing. Okay. Now we're going to look at a particle starting at rest. So particle starts at rest. So this is t equals 0. So t equals 0, rest is at -1, 0. So this is telling me r at 0 is -1, 2. I think it said -1, 0. -1, 2. And with an acceleration vector of 1, 2. If we're starting at rest, what does that mean about the velocity? V at 0 should be not moving, 0, 0, in any direction. Find the location. Find the location, so finding r at, basically r at 2. In order to find r at 2, we have to find r. So if this velocity, so see how it doesn't have a t? This is kind of like an initial condition. So we first start off, by, we have the acceleration vector. We're gonna need to get first velocity and then to the vector function. Okay, velocity is equal to the integral of acceleration. So we want to integrate 1 and 2 with respect to t, which means our velocity becomes t plus c1, 2t plus c2. And using our initial condition, so basically we get 0, 0 equals 0 plus c1, 0, 2 times 0 plus c2. Sub it back in, v of t is equal to t and 2t, since both the constants are 0. Then our position vector is equal to the integral of velocity. Okay, so this is going to become 1/2 t squared. We'll just say c3 since we already had c1, 2. And t squared plus c4. Okay, and then another initial condition, also known as a bicondition. We'll just say initial condition. So r at 0 was -1, 2. Okay, subbing that 0 in when there's a t. So we really have -1 is equal to c3, and 2 is equal to c4. So r of t, plug back in your constants. R of t is 1/2 t squared minus 1, and then t squared plus 2. Now we're going to find r at 2. Okay, 4 times 1/2, 2 minus 1, 1, 6. This is the position when t is 2. Okay. You can pause it and try to do example 4. It's basically the same thing. Make sure when you integrate your sine and cosine, you integrate and get a c. It's negative. Okay, so that's what we should get for example 4. Move into example 5. Remember, when an object is subject to gravity, its position s above the ground is given by this equation, where v naught is your initial velocity and s naught is your initial height. Okay, baseball is hit 4 feet above the ground. What is 4 feet above the ground telling us then? It's not. And it leaves the bat at a speed initially. So this is telling us our initial velocity is 105 feet per second, with an angle of 40 degrees to the ground. Okay, so another thing you're going to want to know is that while s is equal to negative 16t squared plus v naught t plus s naught, which this is in feet, that's why it's negative 16t squared. S is the y value, it's the height. So it's going to be where the j component is. To figure out your x value, you might want to remember this triangle. So if we're saying that this is the angle formed, theta is the angle formed with the ground, and we hit the ball at some initial velocity, how can we find the velocity really in the x direction? We know theta, we know the hypotenuse, we want to find the opposite. So the adjacent. So you want to find the adjacent, you would use cosine. Cosine theta is going to be equal to that x value over your initial velocity, and solving for that x value gives us v naught cosine theta. You could do the same thing for the initial velocity in y. So this is pretty helpful in this problem to figure out the velocity in the x direction. So if this is the velocity in the x direction, this is a constant, and we're saying we're going to have to integrate that to get the x value in the position. So when I integrate a constant with respect to t, I'm just going to get that value times t. And then my y component, j component, is going to have your initial velocity this is your initial velocity in the y direction. t plus. Okay, so our initial velocity is going to be 105 cosine our initial angle, 40 degrees. 105 sine. Guess I should have had like initial height there. Okay. Determine how high the ball goes. So this is the maximum. So finding the maximum, we want to find the y value, maximum y value. And let's pretend we don't have a calculator or Desmos to find this. So what else could you use? What calculus helps you find the maximums? Taking the derivative. So y prime t is equal to negative 32t plus derivative of t. I'm not taking the derivative of sine and making it cosine. This is a constant. This whole thing is a constant. So then I'm going to have 105 sine 40. Okay, we want to find the maximum when the maximum happened. So we're going to set the derivative equal to 0 and solve. Subtract, divide by negative. And beep boop beep boop boop. Seconds. So maximum happened around 2.1 seconds. So it's the time when it reached the max height. What is the actual max height? Where would you think about where you need to substitute this in? So the max height is happening at the time 2.1, but we need to plug in 2.19 into the y value. 0.9, I should say. Okay, there is a 12-foot high fence 325 feet from home plate. Is the ball a home run when they hit it that far? Oh, this ball in general, is it a home run? So we have to figure out how long will it take this hit to travel 325 feet. So you're really trying to go 325 feet in the X. You're trying to travel horizontally 325. So set X of t equal to 325, and you're just dividing 325. 5 cosine 40. And you get, it's going to take about 4.04 seconds. And so if it's taking 4.04 seconds, then we're going to say, will the ball go over the fence? aka is y at 4.04 greater than 12 feet. And again, you can definitely use Desmos for this usually. I'm just substituting it in so that way, if you look back at it later, future you is not confused where these numbers are coming from. All right, you get 15.49 feet. Yes, it's a home run. Okay, it's kind of like more of the same type of thing. On example 6, 7. Let's see what's going on with these. You should maybe try to pause this to see if you can get the same answers as me. The water from a fire hose is discharged at a maximum rate of 80 feet per second from a height of 4 feet from the ground. Rate means velocity. 4 feet from the ground. A firefighter can get 25 feet from the burning building. They shoot the water from their hose at an angle of 45 degrees. What is the max height that the water can reach? Well, first, maybe we should write down up here, R of t is going to be your V naught t and your negative 16 t squared plus flux t plus your initial height, which we said was S before. Okay, and remember, flux, void, and V naught. If we know the angle, and this is going to be your initial velocity times cosine at that angle, and this is your initial velocity times sine at that angle. So you're going to have 80 cosine 45t, 80 sine 45t, and what was the initial height? 4 plus 4. Which really means we can simplify, because we do know the cosine and sine at 45 degrees if you want. Cosine at 45 degrees is square root 2 over 2 times that 80 is good. We're going to have 40 square root 2 t, and we're going to have negative 16t squared plus 40 square root 2 t plus 4. What is the maximum height the water can reach? So we need to find y prime. Taking the derivative, set the derivative equal to 0. Solving for t. What's our time unit? Seconds. Which takes 5 squared 2 seconds to reach its max. 5 squared 2 over 4, I should say. All right, so it's max height. It's 54 feet. And on B, the building completely burns down and the firemen are shooting water on the wreckage. How far into the wreckage can the water reach? So if it burned down, what's the height of the building? So the height of the building would be 0. That means that the y is 0. We have to find what time has a y of 0. You could complete the square, or you could quadratic formula. I think I'll just use my calculator on this one. Which one makes sense? This one makes sense. So it took 3 seconds for the building to burn down. How far into the wreckage can the water reach? It's talking about x at t. So it's saying we're shooting 25 feet, but remember it did have, here's the building. And it says a firefighter can get 25 feet from the building. So if they can shoot a total of 203.9 feet, how far into the wreckage is that? They actually got 178.92 feet into the wreckage. Okay, and this one's kind of fast. Find a projectile. A projectile is fired from the ground level at an angle of 10 degrees from the horizontal. Find the minimum velocity to if the projectile is to have a range of 100 feet. What do we think a range of 100 feet is meaning? Oh, and it's ground level. So ground level means S naught is 0. So our R of t is going to be V naught cosine theta t, and then negative 16t squared plus V naught sine theta t plus 0. And we got our 10 degrees. Have a range of 100 feet. We want to figure out the range of 100 feet means to move 100 feet horizontally. We need to figure out what is, we have a 10 degree, we need to figure out our initial velocity to make that happen. The minimum initial velocity. What is the height if the range, at range, the height would be 0. So we're basically saying negative 16t squared plus V naught sine, we'll put the 10 degrees in there, should be equal to 0. Okay. Solving for V naught. And then we also are saying V naught cosine 10 degrees should be equal to 100. Solving for V naught again. Okay. And we're sort of have a proportion now because we have V naught n equals V naught. So you have two different equations. You could absolutely solve this by hand, but I mean, like, why would you want to? Now let's try to do this on Desmos. I'll just want to do subscript on iPad. Forget how to do this. Shift dash works on my keyboard to do the subscript, but I'm not seeing that option here. What the? well, you put a subscript and then you would have cosine 10. Remember, then we're going to put the squiggle, and then you'd have 16x with a subscript over x with a subscript, like the same subscript each time. And then sine 10. And I already have it solved, but you're going to get, if you had done it, I guess we should instead, since I can't get this to work, but I'm sure you can because you're actually on Chromebooks, hopefully. And we need to be in degrees. Try and do like the shortcut. It's very annoying. Oops. Squared x sine 10. Okay, so where are they intersecting each other? Would have been better if we had gotten the subscript to work, but it appears to be at 1.0497. It's a little anticlimactic. I'm sure there's a way to actually do it, but t equals 1.0497. There's another place where they intersect, but it's negative, so we're not going to write that value down. And what is the minimum velocity? Okay, so substituting that into either of those equations, make sure you like close your parentheses for the cosine. You're gonna get 7257 velocity. So what would we be doing at feet per second? Okay, and that's that.